Can you see the screen now?
Yes.
So this is where we stopped yesterday. Now we'll move to our new topic, which we call tilings on surfaces and the Euler characteristic. So we start by defining the tiling. A tiling on a compact surface is just an arrangement of finitely many polygons on X which satisfy the following two properties. The first property is the polygons must cover X. In other words, they cover the whole surface. Second one is that if the polygons meet, so this second one says that if the polygons meet, they do so either at vertices or along complete edges. So we can't have a vertex in between. They must meet at the vertices only or along complete edges. So that completes the definition of a tiling. But we have some more terminology. We can say the polygons that make up this first part are usually called the faces of a tiling, and the vertices and edges of the polygons are simply the vertices and edges of the tiling as well. Now, if the polygons can be of different sizes, and a polygon with A edges will be referred to as an agon. So if it has 4 edges, we refer to that as a fourgon. It has 10 edges, we'll say it's a tengon, and so on. That's a terminology we shall use. I think someone is trying to join. Let's see if we can admit them. So that defines the tiling on a compact surface. We'll see some examples of tiling. So here is an example of tiling on the 4 different tilings on the sphere. So this one, let me make that larger. Can you see the screen? So here is the first tiling on the sphere. It actually is just what you would call, it's the same as the tiling you get on a cube, but it would fit on a sphere as well. So what would make it different on the sphere is that you can make these lines will go along the sphere. These lines that join the corners or the vertices will go along the sphere. So clearly you can see that these faces, they only meet at vertices or along complete edges. There is no overlapping, there's no vertex in the middle somewhere. It's usually right at the end of the edge, and they all meet along complete edges or if not at vertices. So this tiling is all made up of fourgons, or if you like, rectangles. The faces are all 4-sided. This particular one is made up of faces that are all 4-sided. So here is another tiling on the sphere. So what happens with this one is that you have the cube, then you add one more point up here. Then you have edges moving from that point to all the edges on the top face. So now you remove the top face and replace it with 4 new faces. So that's what you have here. The second one has replaced the top face with 4 new faces. So this is the top vertex. So you can see there's one line going to this vertex, another line going to that vertex, another line going to the vertex at the back, and one more line here going to this vertex in front. So we have removed the top face and replaced it with 4 more by just adding another vertex here. So how many? Here now we have a mixture of faces. Some faces are triangles, others are rectangles. So the triangles, we have 4 of them up here. And how many rectangles do we have? Hey, hamwezi kuhesabu bwana. How many rectangles do we have as faces on this tiling? So don't be fooled by the straight lines. This can actually be a tiling on the sphere. You can stretch the straight lines to go along the sphere if you want it to look like it's on a sphere. For now, it's more convenient to draw them as straight lines, but they don't have to be straight. They can go along the sphere, so they can be curved so that they stick. The lines, the edges actually go along the surface of the sphere. So have you finished counting how many faces that are four-sided are on this tiling, this B?
7.
7. Okay. Everyone agrees, I think. So here is the last one. This one may not be very clear. The diagram from the book. So this one has 2 faces. There's just one face down here and another face up here. Then we have put, there are several edges. I think there's one more. There are supposed to be 7 vertices, I think. There's 1, 2, 3, 4, 5, 6. I think there's a 7th one which is not clear from the diagram. There should be a 7th vertex here. So it has 2 faces. How many edges will it have? Meshindwa. So we'll go back to the presentation. So if you use the first tiling, if you use this as a first tiling on the sphere, then you end up with a structure of a cube which has 6 faces, 8 vertices, and 12 edges. If you check the second one, it will have 9 faces. It has 5 squares and 4 triangles. So where was that person who was saying 7? We would like to show us how you counted 7. Not clear. So it will have 5 squares. There'll be 4 faces that are up here, and then the base will be the fifth face. So that's 5 squares if you're working with a cube. Then if you look at the top, you have 4 triangles, so total of 9 faces. Number of vertices will also be 9. And if you count all the edges, it will be 16. So this last one, it has 7 vertices, but you can't see all of them because the diagram is not so clear. I will try to draw this by hand so that I replace this diagram by one that is drawn by hand so that you can see everything clearly. But it has 2 faces, one at the bottom, one at the top, and the 7 vertices and 7 edges. If you count the edges, there will be 7 in total. So this is an example of 3 different tilings on the same compact surface. So you can have more than one tiling on the same compact surface. In this case, the compact surface is a sphere, and all of these are tilings on the sphere. And if you go back a step, you will see that they satisfy both properties. The polygons cover X, so there is no place that is left uncovered by the polygons, and they all meet either at the vertices or along complete edges. So we shall make the following definitions. If we have tiling on a compact surface, we shall use the letter V to denote the number of vertices. So if you see the letter V, V will be equal to the number of vertices. The letter E will denote the number of edges on the tiling, and F will denote the number of faces of the tiling. So this theorem is also a very useful one. It's called the basic tiling conjecture. The basic tiling conjecture says the following: let X be a compact surface. Then there is an integer which is denoted by chi of X, and it's called the Euler characteristic of X, and is given by V minus E plus F. So this means it's a fixed integer, and it doesn't matter what tiling you have on X, this number will always remain the same. As long as it's a tiling satisfying the two conditions that we gave, then this number will always be the same, and it will be called the Euler characteristic. So we have an exercise. We need to compute the Euler characteristic for the tilings of the sphere in the example, the previous example that we had. So can you compute we have 3 of them to compute. Try computing the first one. Just note down the formula. The formula for computing the Euler characteristic is this: V, number of vertices, minus number of edges, plus number of faces. So I want you to do that for these tilings on the sphere. Can you do that? I'll give you 3 minutes. So compute the Euler characteristic for each of these tilings on the sphere. That is the question. And how you compute is you use this formula. The Euler characteristic, which we denote by chi of X, is equal to the number of vertices minus the number of edges plus the number of faces. So give me some answers now. What do you get for A?
2.
What about B? Who has answered B?
Titus.
You want B, part B. What is the answer? Mmeshindwa?
2.
What?
Still 2.
2.
2.
Okay. What about part C?
2.
2.
Great. So you can see it doesn't change. It doesn't matter what tiling you put on the sphere. The Euler characteristic does not change. It's still 2. So that is true. It doesn't matter which tiling you put on the sphere. Any tiling on the sphere will always give you the Euler characteristic 2. So we can make that claim that the Euler characteristic for the sphere is equal to 2. We shall not prove it, but it is actually true. For the sphere, the Euler characteristic is always equal to 2. So now another point to note: when we have a compact surface, we can construct it from a plane model, and that plane model will usually induce a tiling on the compact surface. Now that tiling that is induced will have exactly one face. The tiling will have only one face. If you check this, the face will just be the parts that you can see on the same face that you can see on the plane model. It will only be one. The number of edges will just be the number of edges in the tiling will be half of the number of edges in the plane model. This is because when you construct the compact surface, usually you will someone is trying to join. Let's allow them to join. So we'll go back to the presentation. So the number of edges in the tiling, as we were saying, will just be half of the number of edges in the plane model. This is because when you are constructing the object using the plane model, you have pairs of edges with the same edge level, and those pairs will always come together. And anytime a pair comes together, it gives you an edge of the tiling. So since there are usually an even number of edges, half of those the total number of edges will be half of that number, because every pair gives you an edge. So the number of vertices usually not clear. You may not be able to tell immediately what the number of vertices will be until you construct the surface. So this is where you're using a plane model to construct the surface. The tiling induced may not be easily determined. The number of vertices may not be obvious. So you'd actually have to do the construction to eventually figure out how many vertices you'll end up with. We shall do an example. I don't know if I got. We shall do that example when we get there. So let's first of all write down this theorem. So let M be the word of length n for a compact surface, and let V denote the number of distinct points on the compact surface corresponding to the two n vertices of the plane model associated with this compact surface. Then this tiling that is induced by the plane model will also give us the Euler characteristic as V minus n plus 1. This is because the number of vertices will be unknown, so we just give it a name. So this V represents the number of vertices. It will not be known beforehand because you can only know it after you complete the construction. The number of edges is quite clear. It's easy to figure out. It's n. And we have also said that the number of faces for this tiling that is induced by the plane model will be only one face. So if you apply the formula for the Euler characteristic, then the Euler characteristic determined by the tiling induced by this plane model will simply be given by V minus n plus 1. So this is still V minus E plus F, but it's because we already know what E is. So E is equal to n, and F, number of faces, is 1. What we don't know usually beforehand is the number of vertices. So that one has to be figured out after you have completed the construction of the compact surface from the plane model. We'll see that shortly. So if you take, for instance, the plane model for the sphere, the short one with only A and A inverse, the length of the word is 2. So there's only one pair of edges. So it means the number of edges will be 1. And number of vertices will be 2. Since the edge is 1, it has 2 vertices at each. It has a vertex at each end, so in total it has 2 vertices. So we'll have a total of 2 vertices, and we can apply the formula to get that the Euler characteristic for the sphere will be 2 minus 1 plus 1. This or should not be there. So it's 2 minus 1 plus 1, and that should give us 2. We can also use a different plane model for the sphere. This is the one that is determined by the cube, this plane model. Now the plane model will have 14 edges. So half of that will give you the number of edges in the tiling that will be induced by this plane model. So number of edges will be 14. Is that correct? So number of edges will be 7. Is that correct? So number of vertices will just be the same vertices of the cube. And as usual, there's only one face because the plane model, the tiling induced by the plane model will always have one face. So when you work out the Euler characteristic using this word for the sphere, you still end up with 2. The tiling induced by this plane model still gives you the same Euler characteristic. It never changes. That's for the sphere. So we can check. Let's see. This is for the torus. In the last class, we, using the circulation rules for compact surfaces, so we showed that when we're using the circulation rules for the compact surfaces, we showed that this word, we're able to show that this word is homeomorphic to the word for the torus. So basically, this word is another plane model for the torus. How you obtain this is as follows. The standard word for the torus will have only four. It has 4 letters because there are these 4 sides. That's the smallest plane model you can do for a torus. So what you can do is add one more vertex here at B and add another vertex here on this side. So what you have 2 more edges. So let's look at the first case. When you're using, so when you add those 2 vertices, you end up with this new plane model. So basically, you treat this as 2 cuts. Instead of 1 cut here, you have 1, 2. So there are 2 cuts. So what happens when you join using this plane model? The first round, these 4 vertices will join to become 2. So there'll be a vertex here and a vertex there. I don't know if this is making sense. There'll be a vertex here and there'll be a vertex there, right? So now when you do the final joining, these 2, now we initially had 4 corners. Now we have 2 vertices. When you join these together, these 2 vertices again will meet to form 1 vertex. So all those 4 collapse eventually, and you have only 1 vertex. We've already figured out the number of vertices here. If you use this other plane model on the left-hand side, this plane model means you will have added 1 more vertex here, another vertex here. So in addition to this other vertex that is already here, the one that will appear here, there will be another vertex at the back. So now with this plane model, the vertices will be 2. With this plane model, the vertices that appear after you construct the plane model will be 2. There'll be 1 here and 1 at the back. Then a line joining the one in the front itself. And another line joining to the other vertex, another one coming around the bottom, back to this other vertex in front. So this plane model will give us 2 vertices. One here, which is the same as the one that was in this first model, but since we have added 2 more cuts, they will join to form another vertex at the back there. So 2 vertices for this one, for this plane model, and 1 vertex for that plane model. So we can go back and try to compute the Euler characteristic for those plane models. So when we go back, if you use this first plane model, we saw that the Euler, the number of vertices will be 2. The number of edges will be half the number of the length of this word. So the length of this word is 6, and we have half of that is 3. So this will give you the number of edges. And the Euler characteristic of M now will be 2 minus 3 plus 1, which is 0. So this tells you that the Euler characteristic of the torus is 0. You get the same if you use the other plane model. The other plane model has exactly 2 edges and 1 vertex. When you complete the construction, all the 4 corners join together to form 1 vertex. So the Euler characteristic for this torus again is 1 minus 2 plus 1 is 0. So this tells you again, it doesn't matter which plane model you put on the compact surface, it will always give you the same Euler characteristic. So here the observation is this, that the Euler characteristic of this M is the same as the Euler characteristic of T. And earlier on we had shown that this word M is homeomorphic to this word for the torus. So these two objects represented by these plane models are definitely homeomorphic. In this case, it's just a torus. So using the same ideas, we have seen already that the Euler characteristic of the sphere is 2. The Euler characteristic of the torus is 0, and the Euler characteristic of the Klein bottle can be shown to be 0, as well as the Euler characteristic of the projective plane can also be shown to be equal to 1. So we have shown for the sphere and the torus. So the other two you will have to take as a gospel truth. Maybe later on we can show that they are true. But these two have those values. So we observe that the Klein bottle and the torus have the same Euler characteristic. But they are not homeomorphic, because the torus is orientable and the Klein bottle is non-orientable. So the two surfaces have the same Euler characteristic, but they are not homeomorphic. So what this tells us is that the Euler characteristic is not enough to determine if two compact surfaces are homeomorphic. So just the fact that their Euler characteristics are equal, it does not mean that the two must be homeomorphic. But on the other hand, if they are homeomorphic, then they must have the same Euler characteristic. So the converse is true. If they are homeomorphic, then they have no choice. But just having the same Euler characteristic does not mean they are homeomorphic. So it's good to take note of that. So suppose we pick a normal form, one of the normal forms for the compact surfaces. We saw that orientable compact surfaces can be written as MT, or M copies of the torus, and non-orientable compact surfaces can be written as MP. I think we even checked that the Klein bottle is equal to 2 copies of a projective plane. Is that correct? We showed that K is equal to 2P. So the Klein bottle can actually be written as a connected sum of 2 projective planes. And in general, all non-orientable compact surfaces can be converted to this form, and orientable compact surfaces can be converted to this form. That includes the sphere if you allow M to be equal to 0. So the sphere is just the same as 0T. So for any of these plane models, when you glue them together, you end up with exactly one vertex. I don't have the figures for now. Just take this as the truth. When you glue the models for this connected sum of M tori and the connected sum of M projective planes, you would always end up with exactly one vertex. So the length of MT, remember T has 4 letters. So if you add it M times, the length will be 4M. So if you are looking for the number of edges for the tiling induced by this word, then it will be half the length of the word, which is 2M. So we can then compute the Euler characteristic of MT as the number of vertices minus n plus 1. But we know that the number of vertices will be 1. The number of edges will be half the total number of labels. So we have 2M plus 1. We end up with the Euler characteristic of MT as 2 minus 2M. Using the same ideas, we also end up with the Euler characteristic of MP as 2 minus M. So anytime we have a non-orientable compact surface and we express it in this form, we can easily compute the Euler characteristic as just 2 minus M. The same for any orientable compact surface, which we can write in this form. Then the Euler characteristic will be 2 minus 2M. Remember, we are working with values of M greater than or equal to 1. Though it still works for the case of the sphere, m will be 0, so you will still get 2. So it still works for empty. Here it doesn't make sense to get 0p. So for the non-orientable compact surfaces, we saw that it's possible to write them also as a connected sum of the Klein bottle and m copies of a torus. It's also possible to have some that can be expressed as a connected sum of the projective plane and m copies of the torus. So these are what we call the alternative normal form words for non-orientable compact surfaces. So other than MP, these are the other words that you can have. So if we again consider values of m that are greater than or equal to 1, you can see here. Again, for these particular plane models, when you construct the surface, don't worry about whether you can see it now. For now, just take this as a truth. When you construct the surface, again, you'll end up with exactly 1 vertex for the word, for the tiling that is induced by the words. So now let's check the length of this word, KMT. Now remember, T has 4 letters, K has another 4. So you'll have 4M plus another 4 letters, which can now be written as 4M plus 1. The number of edges on the tiling induced by this word will be half of this, which is 2M plus 1. For PMT, we know P has 2, it's a word of length 2, and T is a word of length 4. So if you have M copies of T, the length will be 4M plus the 2 words for the 2 letters rather for the projective plane. And the number of edges will be half of this. It will be half the length of the word, which is 1 plus 2M. Then from there, you can compute the Euler characteristic of KMT as minus 2M. I think that's correct. And the Euler characteristic of PMT as 1 minus 2M. So with the results that we have now, we can make some statements. So the first one is that the Euler characteristic of M copies of a torus, the largest value it can have is 2. Then it keeps going, becoming less and less. As M becomes larger, for instance, if M is 2, we'll have negative 2. But they will always be even numbers. So you must take note. This will always be an even number, the Euler characteristic of the torus. And the smallest it can, the largest positive value it can have is 2. It cannot go beyond 2. Now, also, if you consider the MP, then this will be equal to 2 minus 2M. So again, this will be less than or equal to 2. The next one again is less than, the smallest you will have now is what? Minus 1, minus 2 for this one. Then for the last one, I think the smallest you will have is 1. So let's see what conclusions we can make from this. Therefore, we can say that the Euler characteristic of orientable compact surfaces must be an integer that does not go beyond 2. It can either be 2 or less. Right? Now we also check that if you have 2 different values for M1 and M2, then these 2 compact surfaces, M1T and M2T, will not be, they won't be homeomorphic because they will not have the same Euler characteristic. Because we said they can only be homeomorphic if they have the same Euler characteristic. But remember again that just having the Euler characteristic alone is not enough to conclude that they are homeomorphic. Then the last conclusion that we can make is that any integer less than or equal to 1 will be the Euler characteristic of a non-orientable compact surface. So here, I think this may not be correct. It must be an even integer, if I'm not wrong, because if we are working with orientable compact surfaces, this is where we shall be. So this quantity can never be odd. So I should correct that in the slides. But for the rest of them, give you non-orientable compact surfaces, and the smallest out of all this, the smallest possible value that can happen is 1, I think. This one, for this case, the smallest would be 0 when m is 1. Is that correct? I think so. Then the next one, this one, for this type of surface, it's also non-orientable because it's a sum of a Klein bottle and a projective plane, so definitely non-orientable. So here the smallest you can have what here is -2, right? So this one, the smallest you can have is 1. That happens when m is 0, right? So if m is 0, then the smallest that you can have is 1. Then after that, they keep getting smaller and smaller. And it can take on any number less than 1. Here we are, for the orientable one, we are restricted to only even numbers. For the non-orientable one, it's possible to get, so for instance, if you want, the even numbers will all be covered by this. I don't know if this is correct. I need to check. Let's go back to the book. This second part, I have some doubts. Yeah, it has a problem. So my suspicions were correct. Let's correct the problem. So this one is 2 minus m. So this is just m. There's no 2 here. This second line, at the end, we should have 2 minus m. There should be no 2 here. This is just 2 minus m. So that's all. So you can start from 1, go down to 2, 3. This one will give you odd ones. I think these will all be odd. This will give you, since it's just 2 minus m, it will give you both. You keep reducing by 1 every time you increase the value of m. Will increase the whole figure by 1. Will decrease the whole figure. So if m is 1, you get 2, because this will just be 2 minus m. If m is 1, we get 2. If m is 0, although we don't allow 0, if m is 2, we get what? 2 minus 2 will be 0. And that makes sense, because if you have 2p, it's the same as a Klein bottle, and we have seen that the Euler characteristic of a Klein bottle is 0. So when m is 2, we should get 2 minus 2. So just ignore these 2. This 2 is not supposed to be there. So I'm ignoring it completely in the calculations. So when m is 3, we'll have 2 minus 3 to give us -1, and so on. So basically what I'm trying to put across is that if you have a non-orientable compact surface, the Euler characteristic can take any value less than or equal to 1. If you go through all of them, you will see that it's possible to get any value that is less than or equal to 1. But For the orientable compact surface, it takes on values less than or equal to 2, but they can only be even because of this formulation. This can only give you even numbers. So, ladies and gentlemen, that brings us to the end of the class. Iko swali? Hakuna swali? Chola, today you have no question.
I don't have.
You're usually our questions man. Where is Wambua? Wambua, uliza swali bwana.
Sina.
Umeelewa kila kitu? Okay, you have another class immediately?
No.
Yeah, you are free to go anyway. So as much as you'd like us to continue, we have to stop. I know you have the thirst for knowledge. You are ready to learn, but all good things must come to an end. Collins bwana, ongea, uliza swali. Okay, I'll stop recording there.